Yes, ma'am. Okay. Good morning, everyone. A warm welcome to the public lecture series organized by ASTERIA Club of School of Engineering, Danand Sagar University. Today, we have with us eminent personality who is going to tell us about the wonderful world of radio astronomy. The beautiful thing about learning is nobody can take it from you. And today, we are here. We are blessed to have Professor Yashwant Gupta, Center Director at National Center for Radio Astrophysics, TIFR, Pune, who is going to address us about the wonderful science and engineering aspects involved in radio astronomy. Sir, a genial welcome to you. Also, we are blessed to have our beloved Vice Chancellor of Danand Sagar University, Dr. K.N.B. Murthy. Sir, a genial welcome to you. Also, we have here the Chairman of Chemistry and Chairman of Electronics and Communication Engineering. Also, we have Dean of Science and Humanities, Professor P.C. Deshmukh. So, welcome to you all. And I welcome all my dear colleagues and our young buddies who are here to enhance their skills and knowledge. Before I continue, let me introduce our eminent guest to all of you. Professor Yashwant Gupta obtained his MS and PhD in radio astronomy from the University of California, San Diego in 1990. After completing his bachelor's degree in electrical engineering from IIT Kanpur in 1985. Since 1991, he has been working at National Center for Radio Astrophysics of the Tata Institute of Fundamental Research, where he currently holds the position of senior professor. Since 2010, he has been the Dean of Giant Meteor Wave Radio Telescope Observatory, a world-class instrument built and operated by NCRA TIFR, located about 80 kilometers from Pune. In March 2018, he took over as Center Director of NCRA TIFR. His research work focuses on the study of different aspects of pulses and development of new instrumentation and signal processing techniques for radio astronomy. Very recently, under his leadership, the GMRT has received the prestigious IEEE Milestone Award. Sir, it gives me immense pleasure in calling you and requesting you to take over the session. Sir, please.
Thank you so much for the kind words. And once again, let me confirm, you all can hear me?
Yes, sir.
Yes, and I'm now going to put my presentation in full screen mode. I hope you can see it.
Yes, sir.
Okay. All right. Thank you. And a very warm good morning to all of you, both to the senior officials of the Danand Sagar University, and equally importantly to all my young friends from ASTERIA who have joined for this program. And what we will do today is to explore how we probe and understand the universe using radio waves, and we will trace the history of how it all started and what is the status today, with particular emphasis on what is happening in our own country. And then we will also look briefly at what the future looks like. So let's get going. We will start right from the beginning because I understand that there is a wide variety of background of the people who are joining, and not all of you may be fully conversant with some of the finer aspects of astronomy and radio astronomy. So I will try to give you the required introduction before going into the details. So as we all know, astronomy is perhaps the oldest science. It started from the time mankind turned its gaze upwards to try and understand what the heavens look like. Of course, it started by using our own naked eyes, which are the natural detectors for light waves, and all of the processing of the information that we gathered with our eyes was happening in the human brain. But as we'll see how these things changed, the first dramatic evolution came with the invention of the optical telescope. And shortly after it was invented, it was this person, Galileo Galilei, who turned this newly invented device to look at the heavens to see what may be learned, and that revolutionized astronomy from forever. And it's interesting just to trace the evolution of the optical telescope through the ages. So what you see here on the top left is a replica of the small instrument that Galileo used. From there to something that was used by Newton, and then used by Sir William Herschel, and from then on to some of the more modern optical telescopes like the Mount Wilson Observatory, the Palomar telescope, and then, as you can see, to these much larger structures, ending up with what will be the future, the 30-meter telescope estimated to be ready in 2027. And as you look at this, there is one obvious thing, that with time they have been getting bigger and bigger. And so obviously bigger is better. But it's useful to understand why bigger is better. And there are two main reasons, one of which may be very obvious to you, that a bigger telescope will collect more light because it has a bigger aperture. And if you collect more light, then you can see fainter objects. You have the opposite of this. When you go to a dimly lit room where the light is less, you dilate your pupils so that you can collect as much of the light so that you can see in the faint conditions. So this is what is called sensitivity. So the more light you collect with the bigger aperture, the more sensitive is the telescope, and therefore it can see fainter objects in the universe. But there is one other advantage that bigger telescopes provide. A bigger telescope has a higher magnification. Magnification is the ability to distinguish between nearby objects in the sky. It is also called resolution. So if there are two objects very close by, as you know that they blur and look like same, and then if you have a magnifying device, then you can separate out and see them individually. Okay, so this property is resolution, and it turns out that both sensitivity and resolution depend on the size of the telescope. Sensitivity, as you can guess, will be proportional to the total area, that is square of the diameter, because that decides how much light is being collected by the telescope. The resolution, which is a smaller number for the resolution, means that closer objects can be separated, and that goes inversely as the size of the telescope. So the bigger the telescope you make for a given wavelength of observation lambda, the resolution is proportional to lambda by d. And so you would like to build bigger telescopes so that you can get finer and finer resolution. So we'll keep this in mind, but we'll illustrate this with two examples. So a simple example is the moon. So if you look at the moon with the naked eye, you may see an image like on the top left. Just about you can make out some black patches, but not much more detail. And then if you start looking at it with bigger and bigger telescopes, you can see this, that you are able to resolve and see the finer structures on the surface of the moon. And you're also able to make out some of the fainter structures that are present on the surface of the moon. We'll illustrate this with one more example. Those of you who dabble in amateur astronomy will know that Andromeda is one of the nearest galaxies to our Milky Way. And it lies very clear sky conditions. You can just about make it out with your naked eye as a small hazy patch in the sky, something like this in the top left. But as you start looking at it with bigger and bigger optical telescopes, you will see that you can then start seeing the details within the galaxy. And right here at the bottom right, you can make out quite a bit of detailed structure of the galaxy, as well as you can start seeing the fainter sources, whether they are background stars or other objects, or even structure within the galaxy. So these are how bigger telescopes give you better sensitivity and better resolution. Now let us ask the question, is there astronomy beyond optical wavelengths? So optical wavelengths, as we all know, is a part of the very large electromagnetic spectrum, which is a very wide range from the lowest frequency radio waves to the highest frequency gamma rays. And this is an illustration of the electromagnetic spectrum going all the way from radio waves through infrared, visible, ultraviolet, X-rays to gamma rays. And so all of this is there. And the question to ask is, can we get signals from astrophysical objects at this different parts of the electromagnetic spectrum. And there are three interesting questions that one can ask. Can the same object emit or be studied at different wavelengths of the electromagnetic spectrum? It turns out that yes, that does happen. And do the different wavelengths give us different information about the object? And that also, the answer is yes. It is a complementary information that you can get. It is just a bit like if a doctor looks at us, if they look at us with X-rays, they will see the skeleton. If they look at us with ultrasound, you will see something else. If you do an MRI, you see something else, and then you are able to collect all this information and make the best diagnosis. In the same way, if you can observe the same object in the universe at different wavelengths, you can combine the information from there and get a much better picture about the physics of what's happening. There's a third question, that can some objects or phenomena be studied only at some wavelengths? So, the analogy of this is that if you want to probe the skeleton or the bones, then you have to use X-rays. There is no other way in which you can easily study the skeleton or the condition of the bones. And so that is also true, that certain objects can be seen only at some wavelengths. And if you did not have that wavelength for observing, you would not know about the object. And so we'll illustrate this by going back to our favorite Andromeda galaxy. So this is the optical picture that I showed you a short while ago. And this is how it looks like in light waves. And these are images of that same galaxy, all the way from radio to infrared to ultraviolet to X-ray. And you can see clearly all the things. Galaxy is visible in different parts of the electromagnetic spectrum. It does look different in different parts of the electromagnetic spectrum, and it gives you, therefore, complementary information. If you look closely, you will find that there are some parts of the galaxy which are seen only at some particular wavelengths. That requires a bit more careful study of the images. So now we ask the question, well, so how do we then be able to observe the universe at different wavelengths? So there are these two hurdles that come. First, of course, is that you need to have detectors, just like human eyes were the natural detectors for optical wavelengths. We don't have natural detectors. So this had to wait till we learned how to receive the radiation at different wavelengths and be able to detect it. And so this came with technology, whether it is photographic plates for improved optical detection, charge-coupled devices, radio communication equipment, and so on. And we'll see a little bit of that with respect to radio waves. And the second is an interesting hurdle that you can ask, do all wavelengths from outer space reach us? And to understand this, you must just remember the ozone layer, which protects us from harmful UV rays from the sun, which means that any ultraviolet radiation coming from outside is blocked by the ozone layer, which means that you can't study the universe at ultraviolet wavelengths very conveniently by telescopes which are sitting on the surface of the Earth, because the ozone layer will block it. So this is an example of how it works. This is a plot showing the electromagnetic spectrum wavelengths at the bottom, going from gamma rays on the left-hand side to radio waves on the right-hand side. And it shows the opacity of the Earth's environment, atmosphere plus ionosphere. So 100% opacity means those wavelengths will be blocked and not reach us. So what you can see is that there is this part of the spectrum in the optical window where opacity is low, which means those signals can reach us from outside. And then you can see there's one big window over here, which lies in the radio wavelength regime, where the waves can penetrate and reach us. At all other places, they are blocked for some reason or the other. At the very low radio frequencies, they're blocked because of the ionosphere of the Earth. At these places, they're blocked because of the elements present in the Earth's atmosphere, which absorb the radiation. Okay, so the natural expectation was that the next branch of astronomy that would develop after optical astronomy is radio, because you can receive the waves. And you may ask, how do you do astronomy at other wavelengths? And this is illustrated by these on observatories. So you have to build your observatory, launch it on a satellite, take it above the Earth's environment, and then use it over there. in order to study the universe at those particular wavelengths. Okay, so with that, we come to how radio astronomy started. So radio waves were first predicted by James Clerk Maxwell, whom I think we all know about Maxwell's equations. He's the one who developed the theory and predicted from his theoretical work that electromagnetic radiation would exist at all wavelengths, including radio. And it was Heinrich Hertz who proved that radio waves predicted by Maxwell do indeed exist. But after doing that, he declared them to be of no practical use and went on to do other things. And then it was these two gentlemen here, Jagdish Chandra Bose in India and Marconi in Europe, who realized that it would be interesting to be able to generate and receive radio waves. So in fact, though normally we ascribe Marconi as the inventor of equipment for generating and receiving radio waves, it was actually, he was preceded by at least a year by J.C. Bose, who showed that in 1894 in Kolkata that you can actually generate and receive radio waves with equipment that you can make yourself. And so this is an example of his prototype equipment, and we have a replica of this that we keep at the GMRT observatory for visitors to see, which shows how he was able to demonstrate this phenomena. And so this started the field of radio waves, and they were used for radio communications, which is what Marconi realized. And but this led basically to the development of the technology whereby you could detect radio waves. But their use for radio astronomy had to wait for another 30 to 40 years because nobody expected at that time that you would be getting radio signals from objects in the universe. And so nobody was looking in that direction, unlike optical telescopes, where Galileo decided to turn the telescope upwards and see what happens. And so in this case, it was an accidental discovery, which traces its origin to the Bell Labs in the US, where they were testing transatlantic communication systems to communicate between Europe and the US across the Atlantic Ocean. And they were having some problem with the equipment. It was producing some unwanted noise or hiss that was disturbing the communication system and making it difficult to use. And this engineer, Karl Jansky, working in Bell Labs, was given the task to debug this problem and try to understand where is this interference or unwanted signal coming from. In order to find that out, he built this contraption, which is the world's first radio telescope. It doesn't look like that, but it has these detecting elements, and he mounted it on a rotating platform so that he could scan and look in different directions and see where from the surface of the Earth this unwanted signal was coming from. Found to his surprise that the signal was not coming from any fixed location on the Earth, but it was coming from a fixed direction in the sky. And this is a plot of the first detections of this increase in intensity in this trace, which corresponds to the detection of this unwanted signal, which actually is a signal coming from the center of our galaxy. And once he realized that this is a celestial radio source, the radio astronomy was born, and this is 1936. But even then, in the beginning, astronomers were a bit skeptical about what could be learned about the universe at radio waves. And the early work was all done by engineers working in places like Bell Labs and so on, who in their spare time built equipment and pushed the field forward. And this is Grote Reber, who was one of the pioneers, who during his spare time built this thing, which now looks a bit more like what we think when we think of a radio telescope. And he used this to systematically scan the heavens and make what we call the first radio map of the entire sky. And he made some interesting discoveries. So this is what that radio map looked like. And contour map, I think most of you would be familiar with what is a contour map. It shows different levels of a particular quantity. In this case, it is the radio intensity that is being received by the radio telescope, and it shows high intensities along this belt in the sky, which actually turns out to be the belt which defines the plane of the Milky Way galaxy. So if you go and look in the dark skies, you will find this faint belt of stars in the galaxy compared to the rest of the sky, which traces the plane of our Milky Way galaxy. And so not surprisingly, he found a lot of the radio emission coming from the plane of the Milky Way galaxy, with some bright spots like this, the Sagittarius, which actually happens to be towards the center of our galaxy, which is the signal that Carl Jansky saw in his first experiment, and then other bright spots, some of which are objects in our galaxy, some are objects outside our galaxy in the universe, but just seen through the background of our galaxy. So from that beginning, it became very clear to astronomers fairly quickly that the radio sky was very different from the known optical sky. And this is what I was saying earlier, that you can get complementary information about the different objects by studying different wavelengths, because some objects don't show up at some wavelengths and others do. So the brightest radio sources did not have any significant optical counterparts. The brightest optical sources did not have any significant radio counterparts. So clearly astronomers realized that, oh, there's a different way of looking at the universe and learning more about it. And here's an example. So if you look at the emission from our galaxy, if you were outside a galaxy and looking at it, this is the kind of picture you would see in the optical if you're looking edge on the galaxy. So if you're looking edge on to the plane of the Milky Way galaxy's disk, you will see this kind of a thing, because most of the optical emission comes from stars and gas and nebulae in the galaxy, which lie predominantly in the disk of the galaxy. But if you look at the galaxy in a similar manner from outside in radio waves, then you see quite a different picture. You still see a good amount of radiation coming from the disk of the galaxy, but you can see that it is no longer such a thin, confined disk, and there is much more radiation coming from further away from the disk of the galaxy, including some objects which are going out to significant angular distance away from the galaxy. And that is because it's a different population of objects. In this case, there are very highly energetic electrons and other particles which give rise to this radiation, which can spread out far away from the plane of the galaxy, unlike the stars and the gas in the galaxy. So this then is basically because the physical processes giving rise to radio emission are very different from that of optical, and hence sources look very different in the radio and optical. And the radio astronomy thus gives a new window to observe and understand the universe. We won't go too much into the details of that, because that goes off into the details of astrophysics. What we'll do is we'll come back and ask, how does a radio telescope work? And then we will get a better feel of the engineering that goes on behind this. So in a very simple sense, radio telescope is basically the same as your satellite dish receiver. And then you may say, oh, that's interesting. But there is a very big difference. Our satellite dish receiver receives signals from man-made satellites, which we have launched. And they are very strong signals that we have put there, so that with a small dish, you get enough sensitivity that you can pick up the signal and detect it easily. But the signals coming from faraway objects in the universe, which are billions and billions of light years away, are very, very weak, much weaker than what we are used to. So, so much so that we have a special unit to measure this strength of radio sources. It's called 1 Jansky, in honor of Carl Jansky, 10 to the minus 26 watts per square meter per hertz. Now, that's a very small amount of power. And if you understand electrical engineering, a typical radio telescope of, say, few tens of meters in diameter would collect power which is minus 100 dBm, where 0 dBm is 1 milliwatt of power, and a dB is a log scale, as you all know. So that's a very, very weak signal. And if you want to look at it, such a typical radio telescope continuously observing a source of, say, 1 Jansky in strength, in 1,000 years of continuous operation, it would collect only 1 millijoule of energy. Okay, so that's, that's much. You spend much more energy in just heating your morning cup of tea, the water that you heat for making your tea. So it's a challenge to pick up these very faint signals, amplify them. And what makes it difficult is when you pick it up and start to amplify it, there is noise that gets added. The noise comes from electronics. We all know electronics devices have their own intrinsic noise, whether it is noise in a PN junction or many other kinds of noise. And that then tends to drown the signal of interest. Noise also comes from outside, some of it from the sky itself, some from other man-made activities happening around the telescope. And so you have to then build low noise electronics, which adds minimum amount of noise to the incoming signal, so that when you amplify it, you have a good chance of finally detecting the signal of interest. So what happens in order to get enough sensitivity, we have to build large antennas, several tens of meters in diameter, unlike your simple small satellite dish receiver. And you have to build very high quality, low noise electronics so that you can minimize the amount of noise that you add. And finally, to further increase the signal to noise, many of the sources that we observe are emitting over a wide range of frequencies, unlike your man-made sources, where each TV channel of your transmission will occupy a certain narrow bandwidth. Many of the natural sources can transmit over hundreds of megahertz of bandwidth. So if you increase the amount of hertz over which you pick up the signal, you'll get more watts. And so we increase the signal by using as large a bandwidth of observation as possible. And the other thing that happens is when you have signal and noise added, if you integrate the signal, so these are sources which are on all the time. Again, on astronomical time scale, sources remain on for millions of years. And so if you go and observe the same source for a few hours, next day for a few days, you can keep adding that signal from the source. When you add signal, you also add noise, but it is well known that the signal grows linearly with the amount of time that you add. The noise, RMS noise power grows only as the square root of the time of integration. So you gain in signal to noise as you increase the time of observation. So these are the basic techniques that we use in order to increase the sensitivity so that we can see the faint sources. You remember the first few slides when we talked about the sensitivity. Now, but there is this other problem, which is the resolution. And as you remember, the resolution goes as lambda by d. So the difference compared to optical is that our wavelengths are much, much longer. As you would have seen in the electromagnetic spectrum, we are operating at wavelengths which are millions times longer than optical. And therefore, even for a 100-meter size telescope, which is quite large, example is shown here, operating at a 1 meter wavelength, which is a 300 megahertz radio frequency, the resolution turns out to be half a degree. Half a degree in the sky, an angle of half a degree is 30 arc minutes. 30 arc minutes happens to be the angular size of the moon in the sky. What does that mean? That means that if you take a 100-meter size large antenna like this, point it towards the moon, and ask, will I be able to see any detail as I scan the telescope across the moon? Answer is no. You will see a blurred image of the moon like this, like we see with the naked eye. And you can't get this kind of image, which is seen with the smallest of the optical telescopes. And so here's another example. This is our Andromeda galaxy that I showed you earlier, the radio image. But if you observe it with this kind of an antenna, this is the blurred image that you would see. That means there is not enough resolution to make out the detailed structure of the galaxy. So as you can see, this is a major problem or obstacle for radio astronomers, because it's very hard to build individual antennas much larger than 100-meter kind of size. This is a 300-meter size antenna. It is fixed in the ground. You can't steer it and move it in different directions, and it can only observe sources as they cross the meridian and with a small range of angles around it. So this was a big practical problem for radio astronomers. Still, a solution was found, which is called aperture synthesis, where it was shown that in order to synthesize a telescope of large size, as far as resolution is concerned, you can do that by building many, relatively smaller telescopes and spreading them out over a large region on the surface of the Earth, and then collecting the signals from all of them and properly synthesizing the signals in order to reconstruct an image whose resolution would be comparable to resolution that you would have got with a single antenna whose size was equal to the extent of the array. So in that formula, D, the size of the individual antenna, is now replaced by the largest separation in the array, ds. And so now you can see that you can build smaller antennas. As long as you have enough land, you can spread them out over a large area, and then work out how to bring the signals back from all of them to a common place where you can process them together and synthesize it. And this was a novel idea that was worked out. It was important enough that its originator, Sir Martin Ryle, got a Nobel Prize for this, for developing this technique. And so what this requires is, and this is a bit more detailed, but this is interesting for those of you who understand signal processing. Basically, the image is being synthesized in the Fourier domain. If you take a two-dimensional Fourier transform of the image and look at the various Fourier components, then one pair of antennas in the array, depending on their separation, measures one Fourier component of the image. It can also be compared to the Young's double slit experiment, which some of you may have encountered as a basic experiment in physics, when you illuminate two slits and get a fringe oscillatory intensity pattern on the screen. You can think of two antennas behaving like a slit detector. But whichever way you look at it, this technique requires you to bring the signals from each of the antennas and process them in a pairwise fashion. So if you have n antennas in your array, you have to do NC2 such blocks of electronics for signal processing, where you cross-multiply the signals from every pair of antennas in what is called a correlator, and then you save the integrated results on the computer, bring them together from all of the pairs of antennas, which are measuring the different Fourier components, and you do a two-dimensional inverse Fourier transform to get the image. So it is a bit complicated. It's a fairly sophisticated technique. It has both real-time calculations in electronics and then offline calculations, which are done when you make the image. But it produces dramatic results. So this is an example of a radio galaxy called Cygnus A. This is an image made with the best possible resolution that the single dish antennas could afford before this. I showed you this Y-shaped array of antennas, which is called the VLA in the USA. Before that was built. And once that was built, this is an image of the same object that was made. Of course, the top one is a contour plot like I showed you earlier. This one is a grayscale image, but you can still do the comparison. And what you can see is the resolution here is much better. You can make out much finer details of the image. You can see that the central object is a very compact dot, and that you can see that there are interesting jet of radio emission going from connecting the central dot to these lobes, which are part of the radio galaxy. So this then allowed radio astronomy to be competitive with all other branches of astronomy, particularly optical astronomy, to be able to study objects in fine detail. And array telescope is what has now become the norm. There is also one mode of the array telescope where you just combine the signals together to make it look like one large single dish instead of doing this pairwise correlation. And that is useful for studying very compact objects like pulsars and so on, where the resolution, you will never be able to make out the details. It's such a compact object, but you want the full sensitivity to do this. So now you can ask this question, well, how far can you extend this concept of array telescopes? And so I showed you something like the VLA, which is about 20 kilometers in extent. But you can now do this for antennas spread out over the entire continent, for example. And so remember, the larger the separation between the antennas, the better resolution image you can make. Okay, so this gives you a very high resolution. Now you can, from arc minutes that we talked about, you can go down to arc seconds and milli-arc seconds by having antennas spread out over very large distances. You can ask, well, how do you manage to get the signals from all the antennas together to a common place for doing the processing? And in the early days, what was done is that the voltage coming out from the final receiver was recorded at each location, which is very, very high data rate of recording, but it's possible to do that. And then you carry over the recorded data, whether it was tapes or later on hard disks, to a common location, and then do this playback and do the correlation analysis. Today, it is possible with optical fiber connecting all the places, far away antennas, to bring the signal together to a common place over optical fibers. And this technique is called very long baseline interferometry. And this is successfully used in order to get this. Now you can ask, can I extend this? Yes, you can. You can do this between continents. So here's arrays of antennas in North America, arrays of antennas in Europe, whose signals can also be combined and get very high resolution images. You can ask, well, can you jump and do this? That is, combine signals with antennas which are put in space with those on the ground, and now you will have baselines, this longest distance, which is now tens of thousands of kilometers instead of 1,000 kilometers. And this is in principle, as you can see, is possible. In practice, it's a bit difficult, but it has been done. There have been a few, one or two projects where antennas have been built, put on satellites, launched, and then unfurled to give it the final shape like this, and then used in coordination with antennas on the ground to observe the same sources and get a very high resolution. So this is an image. You saw that central dot in the radio galaxy that I showed earlier. This is now zooming into what that central dot looks like and asking what is that core of the galaxy contain and what is the structure. And you can start making out finer structure over there and see that how the jet of energetic particles is moving out from the core of the galaxy towards the lobe. So, this all allows you to get more into the details of the physics of what's going on. There is one other aspect which is possible predominantly with radio waves, which is searching for extraterrestrial intelligence. As we all know, man has always wondered, are there intelligent beings in other places? And people have asked if there were, and if they were signaling, then what would be the most natural media for signaling? And people believe it would be radio waves, because that's how we communicate with each other, using radio waves. And so there's a branch of astronomy which tries to see if we can pick up any signal from extraterrestrial beings. And some of radio telescopes spend some fraction of their time searching for extraterrestrial intelligence. Some are built exclusively for doing that kind of work. And I think many of you may be familiar with programs like SETI at home, where you can contribute this effort by providing the spare CPU cycles of your computer at home to analyze the data taken by such telescopes, where they are sifting through to find any traces of extraterrestrial intelligence signal. Now, what we'll do is just trace the growth of radio astronomy in India and take the case study of a modern radio observatory like the GMRT. The radio astronomy in India was started in the 1960s by Professor Govind Swarup at TIFR, and there was also another group at the Raman Research Institute by Professor Radhakrishnan, started a bit later. And there's a long history starting from building simple telescopes in the 1960s, and then to more complicated ones like the Ooty Radio Telescope, which was built in the 1970s, which we still operate and use for science, and then ending up with a really world-class facility called the Giant Meter Wave Radio Telescope, built in the 90s and still operational and recently upgraded. And so we'll zoom in on and study the GMRT in a bit more detail. What you can see here is that the GMRT is a low-frequency instrument. As I showed you, the radio window is quite wide. You can observe from Earth-based facilities from 30 megahertz to 300 gigahertz, and it's difficult for a single radio observatory to cover the entire range, and they're built then to focus on different parts of the radio window, and ours is built for lower part of the radio window, about 100 to 1450 megahertz, and at this frequency is one of the largest facilities in the world. So it's an array telescope. Like I explained to you the concept of why you need arrays. So it's 30 antennas. Each is still quite large, 45 meters in diameter, spread out over a 30-kilometer region. I'll show in a minute what the spread looks like. It was designed and built completely in-house in the country by our group, with some collaboration with other groups in the country during the 1990s, and operational since 2002 as an international facility available for use by astronomers from all over the world. And recently in 2018, we completed a major upgrade, which makes it a more versatile facility with increased sensitivity, keeping it in the forefront on the global scenario. So this is what the configuration of the GMRT looks like. It's 30 antennas over 45, each of 45 meters. And you can see this. So if you travel from Pune to Nasik, the road cuts right through the array, where you have 12 antennas in a central compact array, and the remaining 18 spread out roughly in this Y-shaped structure, with the extent, radial extent being a bit more than 14 kilometers. So what this allows you, by the technique that I described earlier, is to combine the signals from all the 30 antennas and to synthesize a radio telescope of a diameter just above 28 kilometers in size, with a resolution corresponding to that kind of a thing. And this is a Google view. If you do Google, this is what it will tell you. This is the central 1 kilometer by 1 kilometer region, and you can just about make out the individual antennas. This is zooming in, and now you can see them. And these are some of the closest antennas in the array, just about 200 meters separation. And this then shows a view of the observatory. This is the main building, where the signal from all the antennas is brought over optical fiber and received over here, converted to electrical signal, digitized, and then processed as I described in that processing system that is needed. There's a control room over here from which the entire observatory can be controlled by just one person sitting there, commanding the entire observatory and setting up an observing program which could run for several hours and making everything work in a synchronized fashion. This is a view from a nearby hill showing the central antennas in the central square. This is a close-up of one of the antennas. Now you can see what 45-meter diameter means. The antenna where most of the sensitive electronics is located. You need a special high-lift platform of this kind, where the total height it reaches here is 28 to 30 meters in order to access the top. And this is, you can imagine how such a giant antenna would be built. This is how the GMRT antennas were built. They sit on a concrete tower. This itself is equivalent to a 3-story building. And on top, the antennas was assembled piece by piece. And then the main structure assembled here and then lifted up and then hoisted, and then you get the full working antenna. As I was telling earlier, the GMRT was built in the 1990s, and in 2001, it was then dedicated as a scientific facility available for the entire world. This is from the inauguration ceremony. Ratan Tata was chairman of the TIFR Council, doing the honors with the then director of NCRA. And The facility, as I said, is open for worldwide participation. It is used by astronomers from all over the world. As you can see here, roughly 50% of the astronomers using are from India, remaining from many, many different countries from all over the world. And the way it works is that there is anybody can make a proposal for carrying out a certain kind of scientific investigation or observation which fits within the capabilities of the GMRT. And this thing runs in proposals where every 6 months there is a proposal cycle, and people from all over the world put in their proposals for what they want to do. And typically the requests that we get for the total amount of time that people would like to use the telescope for, compared to the time that we have, we are oversubscribed. So the demand is more than the supply by a factor of between 2 and 3 most of the cycles. And so, whenever the demand is more than the supply, it means there is competition, which means only the best ideas, the best proposals are selected by the committee and then allotted time on the telescope for, and then we schedule that for a 6-month cycle for the observations to be carried out, and the data is made available to the people who proposed the experiment. And what are the kind of experiments? It's a whole range of science that such a versatile facility is capable of, from studying the sun at radio wavelengths to looking for extrasolar planets. As you know, today, a lot of search for planets is going around outside our solar system, and radio waves can be used to find such planets. From there to pulsars, exotic neutron stars, to other galactic objects, supernova, remnants, microquasars, explosive events like gamma ray bursts, and then studying hydrogen gas in various ways, because radio window offers the best option to study hydrogen, and hydrogen is the most prevalent element in the universe, and so we can see it in all the way in our galaxy to far off galaxies. And then radio properties of galaxies, radio galaxies, of which I showed you an example, and a very early universe, how it started, when were the first stars and galaxies born in the universe, and so on, and all the way to making an all-sky atlas of the universe at a particular frequency. In this case, one full sky atlas of all sky visible from GMRT was made a few years ago at 150 megahertz, and it's like an atlas where you can go and refer for any information that you want about what the universe looks like at that frequency. And so many new interesting results are there, about 50 papers every year in international journals using GMRT data. Now, as you could have guessed by now, that to build something like this is a culmination of all kinds of technologies. Before you can do science, you have to have all these technologies in place. And as you can imagine, all the way from mechanical engineering in order to build such large antennas, and the servo engineering required to move them with great precision as they track the sky, and then all the radio frequency engineering, the very critical elements which pick up the electromagnetic waves and convert them to electrical voltages, and then the amplification and the filtering and the conditioning of all the voltage signals, and then transmitting them over optical fiber to the central antenna, large bandwidth optical fiber transmission systems, and then the receiver chain which receives the signals at the central building and digitizes them. So we get 20 gigabits per second sustained data rate from all the antennas, and the total real-time computing power is 20 teraflops required in order to do all those computations and reduce the data to a form where it can be written on the disks for offline analysis. And then in order to monitor and control this entire extended or observatory, you need a very sophisticated monitor controls, command and control system distributed over the 30-kilometer range, and then the corresponding control software required to run the entire observatory in a coordinated fashion. And then, of course, the data processing software, which is the software required to take the recorded data and do all the proper calibration and make the images, of which I showed some examples. So all of that is required before you can get these interesting results. But there have been many interesting, exciting results in the now much more than 15. Now we are more like 18 years this has been functioning. And what was realized, of course, even as the first 5-8 years of the initial GMRT, that we should look at the next generation and improve it. And that's what we started around 2012. And in 2018, we finished a major upgrade where we've increased the frequency coverage to be almost continuous from a bit below 120 megahertz to 1450 megahertz, and be able to handle a much larger bandwidth. You remember the bandwidth I mentioned, the larger the bandwidth you can process, the more sensitive the facility. So we can now process 400 megahertz of bandwidth from all the antennas compared to 32 megahertz earlier. And that makes it a much more sensitive facility. And it keeps us as on the forefront as one of the most sensitive radio telescopes in the world in this frequency range. One interesting thing, of course, is that when you have such a powerful facility, you can do many other things, at least a few other things other than just astrophysics. And here is an example where powerful radio telescopes have been used as part of space experiments in order to track the space missions. And all of you who saw on your screens the story of Chandrayaan-2 will relate to this, where so the signal that you saw on the screen from Chandrayaan-2 is actually the radio signal that is transmitted from there and picked up by the receiving stations. In that case, it was ISRO's antennas. But in this case, which was a collaboration that we had with NASA and with the European Space Agency, we were the ground station for monitoring this mission to Mars in 2016 when it landed there, called ExoMars, which was a European collaboration for sending the space probe. Just like this month, there are a few space probes reaching Mars. We were given the task of picking up this beacon from the probe as it made this descent after leaving the orbiting spaceship. The lander module has to come down, just like the Chandrayaan lander module. And this is a very weak signal. So this is like 3 watts being transmitted from Mars at a frequency that was suited for the GMRT. And we were using the array to pick up the signal. And we could actually pick it up and track it. You can see this is the Doppler, which is the shift in the frequency due to the movement of the lander module, the velocity. And this is a critical way of tracking the health, just like you could see the track of Chandrayaan-2 on the screen. And in this case also, unfortunately, just like Chandrayaan-2, that signal was lost just a few seconds before it was supposed to touch down and reach the surface. And a bit like Chandrayaan-2, this also suffered a mishap and it crashed. But this was signal being relayed live from GMRT to the mission control in Germany, where they were monitoring the health of the mission. And they also could then realize that something had gone wrong with the mission. So these are the kind of things which are fun, which can be done with this thing. So now I just wanted to check. I've used up a bit over 50 minutes. So should I just continue with a little bit more about the future, or should we stop and take questions?
I think we can maybe another 5 minutes maybe, because we are having a meeting at 12 actually.
Yeah. So I'll just do it very briefly, and which is basically the next generation is what we call the square kilometer array, a big international telescope, which is going to be much bigger than GMRT. Okay. And no single nation can build such large telescopes. These are all now being built with international collaborations. And so we are part of an international collaboration with 12 other countries, which are aiming to build this next generation radio astronomy facility, which will be located in Australia and South Africa, because they're very radio quiet regions with very little radio noise. And this is an example of the kind of array. 200 antennas of 15 meter size spread out over 150 kilometers. So you should just compare it with GMRT with 30 antennas spread out over 30 kilometers. And this is in South Africa. And this is the part of the array in Western Australia, where these are not antennas, but dipoles, and a field of dipoles combined to make it look like one station. A station can be thought of like an antenna, and then many such stations spread out over 80-kilometer region to be located in Western Australia. And this is an example of the collaboration with different member countries participating, with the global headquarters located in the UK for this project. And work for the design is over now, and from the end of this year, construction is expected to start, and all the countries are then sort of getting prepared to play their role in the construction of this project. And once again, you saw with GMRT, the technologies, when you think of something which is 10 times more powerful than the GMRT, then it really is pushing the frontiers of technology in various areas, whether it is antenna design, sophisticated receivers, extensive fiber network, which is total traffic greater than the internet traffic of the world, supercomputing capability to reduce the data, and sophisticated management and control software. And then in order to process the data, all kinds of modern techniques from machine learning and others to be used for making sense of the data. So I'll stop there with a brief summary, and happy to take any questions that listeners may have. Thank you.
Thank you, sir. Thank you for taking us through a journey of radio astronomy and also GMRT. It was a beautiful session for us. Hope it has enlightened our young minds, and they would use it for better purpose. I request Tanmay Sharma to handle Q&A session. But before that, since shortage of time, we would like to take at least 3 or 4 questions. Tanmay?
Thank you, ma'am. Sir, so there's a question from Professor P.C. Deshmukh. Okay. If anyone in the meet has any questions they would want to ask, I'd request them to ask it right now. Otherwise, we can continue on to the questions from YouTube, because there are 2 questions from there.
Yeah, sure, go ahead. So is that the one which is in the chat box? No, so there Professor Deshmukh is saying that he will send questions by email. But thank you for your comments, Professor Deshmukh. But if you have any quick questions, I'm happy to address them.
I wanted to know the participation of Indian astronomers to the black hole image that we got recently for the Messier 87 galaxy. So
yeah.
Would you comment on that? That is one
Sure.
question I had. I had another one, which is the estimation of the temperature, because finally we seem to be coming down to 3 degrees Kelvin. But then there were some other prior experiments. I think Dickey did some experiments earlier, and then Gamow also did. And they had estimated like 45 degrees, then 50, then came down to 20. So after the Penzias and Wilson experiments, have there been any further changes to this which have ever been suggested after 1965 experiment of Penzias and Wilson, or is that absolutely the final?
Yeah, okay. So both are interesting questions. Both are a little bit in the different frequency regime than where we work. So the imaging of the M87 galaxy core with the black hole at the core was carried out at millimeter wave wavelengths. And as I explained, the radio window is quite broad, and our facility works at meter and centimeter wavelengths. And these experiments were carried out at millimeter wavelengths, again, for the primary reason of getting the maximum resolution. So the lambda at millimeter wavelengths is smaller than lambda at centimeter wavelengths. So even then, you had to go for antennas located in different continents. So these were antennas located in, all the way from Antarctica to South America to North America and Africa and so on. So no Indian facility was involved in that experiment, because none of the Indian facilities work at those frequencies. But there were Indian astronomers who are
Yes.
in these institutions which were involved in those, and so there are certainly Indian astronomers who are authors on that on
Yes,
the
of course.
discoveries.
Yes.
But there were no Indian facilities or observatories involved in
Yes.
that.
All right.
Okay, and then to your second question, so I think you're talking about the microwave background radiation.
Yes.
And as you can tell by the name, microwaves means they are again at higher frequencies than centimeter and meter wavelengths. And there's been a lot of progress since the days of Penzias and Wilson when they first discovered the background.
Yes.
And there have been special experiments like the Cosmic Microwave Explorer, and others which have been mostly spaceborne high frequency instruments, because again at some point in that part of the spectrum the Earth's atmosphere starts absorbing the signals, and they are better done with spaceborne probes. And so there have been special space observatories built and launched for studying this phenomena over the last several decades. And there's a huge amount of progress made in terms of measuring the background temperature to a high degree of accuracy, as well as fluctuations in this temperature on a spatial scale, which has given a lot of this information about the cosmology of the universe that we know today, about the early history, including this composition of things like dark matter, dark energy, and other things. So a lot of that cosmological inferences about the early universe and its evolution and its sort of current state come from those kind of measurements. But again, there's not been too much of participation in India. There have been Indian astronomers who've been involved in some of these projects.
Yeah, sure.
There have been astronomers who have interpreted the data that has been taken by such satellite-borne probes. But most of these experiments have been carried out by probes which have been sent up primarily by the USA.
So do we understand the anisotropy in this?
We understand to the extent that it has led to many new interesting questions about the universe, which we are now trying to understand. So I think, study of astronomy, and in some sense in many other fields also, when you probe deeper, you think you will understand this phenomena. You do, but then it throws up many other new things.
Absolutely,
which then you become your next pursuit. And so,
we know what questions are to be asked, but not necessarily the answers to those.
Yes. So, that's how the pursuit of science goes.
Sure.
Yeah.
Yes. Wonderful talk, Professor Gupta. It's a great pleasure.
Thank you. Thank you so much.
Thank you very much.
Yeah.
Sir, we have a question from Pranav Padaki. He is asking if he's telling that there was one radio signal which was detected, which is dubbed the wow signal, which is not only naturally emitted radio wave, which is not a naturally emitted radio wave. So what are the factors to differentiate a natural signal from a man-made or artificial radio signal?
Yeah, so that's actually a very good question about how to distinguish. And whether the wow signal is really something to be wowed about or not, I'll not get into the arguments of that, but to focus a bit more on what is it that you would use. So most of the natural phenomena signals can be thought of like almost like a random process, in the sense that they are generated by physical phenomena which are by nature chaotic in nature. Okay, whether it is an ensemble of energetic particles in a large cloud that are radiating and giving you the signal, or even the way the sun finally produces emission, it's a chaotic reactions that happen as compared to man-made signals. So it's a bit like listening to noise and then suddenly you hear somebody's voice. Okay, and that's a well-defined signal which has sharp changes and ups and downs, and whether it is in frequency or it is in time. So that is the kind of thing that we use as one of the basis to look for sudden changes in the signal level to distinguish between artificial and man-made signals which would come from an so-called intelligent being as compared to more random natural phenomena signals.
Thank you, sir. Tanmay, can we conclude the question and answer session?
Sure, ma'am.
Yeah, okay. So before I call for vote of thanks, I actually want to congratulate Dr. Radhika, madam, for organizing such a great session and also the coordinators. I request Mayank to deliver vote of thanks. Mayank?
Yes, thank you, ma'am. I begin with thanking our distinguished speaker of the session, Professor Yashwant Gupta, Center Director at NCRA, Pune, for enlightening us on the different aspects of radio astronomy. We are grateful to our respected Vice Chancellor, Professor K.N.B. Murthy, Registrar Dr. Puttamadappa, and Dean SOE, Dr. A. Srinivas, for the immense support in organizing this lecture. We also thank Dean Science and Humanities, Professor Deshmukh, all department chairmen, and all the faculties for their presence. A special thanks for Dr. Radhika for managing and organizing, and to all the organizing committee coordinators for making this event success. Last but not the least, we thank all the student participants and all of those who have joined our YouTube channel. Thank you one and all.
Thank you, Mayank. Thank you, sir. Thank you. It was like a complete knowledgeful session for us, even for us and students. Hope they will make best use of it. Thank you, sir.
Thank you. And also students, you are encouraged to contact if you have any further queries or questions or would like to discuss anything.
Thank you, Professor Gupta. I feel many students will be motivated to implement the engineering skills and science understanding into radio astronomy. You have presented it very well. Thank you very much, sir.
Thank you.
Thank you all.